Hello, my name is Victor, and in previous videos we have learned about the various trends across down the group and across the period of this periodic table. Now in this video I want us to we learned about the atomic size and radius and also reactivity. It is important you watch these videos first before you watch the current video. Why? Because when you want to learn about melting and boiling points and also electrical conductivity, we will continuously refer to the atomic size or atomic radius of an element. So first, we will talk about, let me redraw this. We said that the whole of this is decreasing atomic radius. Here is increasing reactivity. And also we say this is increasing reactivity. We talked about this is increasing atomic radius, increasing reactivity, and increasing reactivity for nanometals. Alright, let us talk about electrical conductivity first, the last one, then we will go to melting and boiling point. So, electrical conductivity. We know electrical conductivity is supported by mobile ions. So, for metals, sodium, let us draw well this one. This is what we call metallic structure. This is sodium, this is magnesium, and this is aluminium. When we talk about electrical conductivity across the period, we don't talk about it down the group. For sodium, positively charged nuclei is surrounded by each atom contributes. The electron arrangement for sodium is 2, 8, 1. So this one electron revolves around in this metallic structure. It does not just stay in one atom when it is a metal, when we are holding a metal. So positively charged nuclei contributes one delocalized electron. We have another positively charged nuclei carrying another electron. We also have another positively charged nuclei contributing one electron. So this electron, the delocalized electron, is pulled to the various nuclei. Multiple of nucleus is nuclei. It is being pulled continuously to all this. However, for magnesium has it is also positively charged. Not necessarily important to write 2 plus. However, the electronic arrangement is 2H, 2. So it has 2 delocalized electrons in each proton. So you have an electron there, an electron here. You have an electron here, an electron there. And you also have this, an electron there and an electron here. So let's talk about aluminium. You draw again 3 positively charged nuclei. One nucleus contributes to 3 electrons because the electronic arrangement is 2, 8, 3. So this one has 3, this one has 3, and this one has 3. So we are going to use this diagram to learn both electrical conductivity and also melting and boiling point for metals across the period. Now, if the number of electrons, if electrons are responsible for carrying electrical charge, then the number of electrons in an element or in the number of delocalized electrons in the structure or a piece of a metal, suppose this is a metal. So the number of electrons in this, delocalized electrons in this piece of metal, then would affect the rate of carrying electrical charge. In other words, we are saying the more the delocalized electrons, the more the number of delocalized electrons, the greater the electrical conductivity. Therefore, we are saying aluminium is a better electrical conductor than magnesium. Magnesium is better than sodium. Aluminium is better than them all. Aluminium is better than all these elements. Therefore, if you were to add in your periodic table, if you were to add a chain, you would write this up to here for group 3 and say increasing electrical conductivity. Increasing electrical conductivity for metals. Nanometals do not conduct electricity. Only metals conduct electricity. Any other substance that conduct electricity are not molecular, ionic compounds like sodium chloride. When it is in molten form or in solution, the compound exists as the components exist as mobile ions. Now it is these ions that carry electrical charge. However, atoms themselves do not carry electrical charge. So now you understand why aluminium is used to make electrical cables, overhead electrical cables. There are several factors. One, it is a good conductor of electricity. Two, it is light. It is relatively light than iron and other elements. Therefore, lower density makes it possible to be used as overhead cables, not like copper, which is used in not indoors, in the houses and buildings, the cables in these houses. The other factor, it is ductile. It is easy to make as a wire. And lastly, is that it does not easily corrode, because aluminium reacts with oxygen to form a protective or non-corrosive layer of aluminium oxide that's not soluble in water, therefore protecting the entire wire. If it is iron and it is put in the open, it is rained on to rust, but aluminium does not rust. Now, we said increasing electrical conductivity facing this side. Increasing reactivity is this side, increasing electrical conductivity this side. Alright, another thing, let's talk about, so we are done with the electrical conductivity. So we are done with this, we are done with this, we are done with that. Let us talk about melting and boiling points across the period for metals. Across the period for metals. Before I wrap this diagram, we could use it. So, the number again, we said these negatively charged nuclei are attracted to multiple. These negatively charged electrons, are attracted to multiple positively charged nucleus because they are just revolving. Again, the more the number of electrons, the stronger the metallic structure. It will be hard. You know, boiling and melting involves breaking these bonds and making this loose, this atom and another atom become loose or not close to each other. So therefore, when you are talking about melting or boiling point, it will again be affected by the number of delocalized electrons in the metallic structure. In this metallic structure. So therefore, the more this one is harder or has a higher melting point than this has higher melting point than this. So for metals, as you go this way, we have said increasing electrical conductivity. We should also add, we had to put this. So So as I had requested you, you need to write this notes in your book so you can understand better. As you go this, you write increasing melting point and boiling point. Increasing melting point and boiling point for metals. Remember, this is metals. Again, also this is metals. And this is metals. But this one is for all. The atomic radius is for all. However, increasing melting point, increasing electrical conductivity, increasing is facing this side, reactivity, going this side. And we talked about losing the number of electrons required to be lost. So we have talked about that this one will have a higher melting point. So let us talk about, we can now comfortably delete this, we will not use it. The rest we are going to use the atomic size. Now let us continue, complete discussing metals. Let's talk about melting point down the group like this. So let us compare lithium and potassium. Lithium has this electronic arrangement. Oh, we might have needed that diagram again. However, let us use we are going to draw again. Potassium is we can compare sodium. Let us compare these two so that it becomes easier to draw. So this one is 2H1 and this one is 2,1. So let us draw the metallic structure of both. So when you have this for sodium, and here we have for lithium. So what are we saying? That this atomic size is smaller than this one. This one is larger. So the positively charged nucleus will be like this. While for this will be bigger. These electrons So we have the number, we have talked about the number of delocalized electrons affecting the strength of the metal. In that metallic structure, we have said the more the number of delocalized electrons, the stronger the metallic bond. What about when we have the same number of delocalized electrons in the metallic structure? What will affect the strength is the atomic size. Because this electron is being attracted by the nucleus of these atoms, the nucleus. This one is at a distance. So therefore, when you have a longer distance to be attracted, then the strength is not so strong. Actually, what keeps them together is because each electron is being attracted by multiple nuclei of these atoms. Therefore, it just puts them together. They cannot be apart. So the longer the distance, the weaker the bond. The longer the atomic size, the bigger the atomic size, or the longer the atomic radius, the weaker the metallic strength. And therefore, less energy is required to melt this. So this one has lower melting point and boiling point. This one has higher. So if you are talking about increasing, we could draw with a black pen, yes. So this one, as you go up, you are increasing melting point and boiling point. As you go up, you are increasing melting point and boiling point for metals. So, what have we talked about this? We have talked about electrical conductivity. We have said it increases going this way. We have talked about melting and boiling point. We have said it increases going this way and also increases going up for metals. So around this point, up to this point, we are saying these are more have higher melting point. As you also go up, they have higher melting point. So let us talk about nanometals now. Nanometals do not conduct electricity, so we are going only to talk about the melting and boiling point for nanometals. So the diagrams we drew here, we were talking about the metallic structure. When we are talking about melting and the boiling point for metals, we have to think about the metallic structure. That should stick, metallic structure. But when you are talking about nanometals, do they have metallic structure? No. What do they have instead? They have molecular, intermolecular forces. So, for oxygen, for example, oxygen will bond with another oxygen, so it will be written as O2 to form a molecule. Then this O2 will bond with another O2. So, what will affect the melting or boiling is this bond, and that is when most nanometals are gases, because they have weak intermolecular forces. Weak. Example is weak van der Waals forces. These are intermolecular forces. Another intermolecular force is called hydrogen bond. Hydrogen bond. This one is stronger than weak van der Waals forces. It is present in H2O. H2O. When you have this, a molecule of H and H here, H and O in the center. This is O, H and H. The bond between them is called hydrogen bond because it is hydrogen and connects hydrogen and hydrogen. Now, so that one I was just explaining. So, what will affect the strength, even just for the weak van der Waals forces? We are comparing weak van der Waals force of oxygen and that of sulfur. Or let us talk about fluorine. We have fluorine F2 as this. And then we have chlorine. Let us try to draw them comparing the sizes. Chlorine has a larger atomic size. So, inakaa hivi. So this one has a larger atomic size and therefore larger molecular size. If the atom is large, generally, then the molecule will also be large. So, what happens is that the larger the molecular size, the stronger the intermolecular force. So, stronger intermolecular force is present in larger molecules. Larger molecules have stronger intermolecular force. Therefore, when you have stronger intermolecular force, it requires more energy to break or weaken these bonds. So therefore, this one will require more energy, or therefore it will have higher melting point. This one will have lower melting point. So this one was increasing reactivity. It was going up. Now we are going down and say going down, we are increasing melting point and boiling point. This one is increasing melting and boiling point down the group. So note the difference. So generally, for most, don't generalize. For most, the behavior of metals and nonmetals is different. See, increasing melting point, this one is increasing going down. We talked about increasing melting point going this way. So let us look at these two. Let us compare this group, phosphorus, sulfur and chlorine. Remember, there is this point, this one in green, we said decreasing atomic radius, just decreasing going this way. So chlorine has a smaller radius than sulfur. Chlorine has a smaller radius than sulfur. Sulfur here will have a little bit larger radius. Therefore, with the larger molecular size, we talk about larger molecules, larger molecular size, will have stronger intermolecular forces. Therefore, this will require more energy to break or weaken in melting and boiling than chlorine. So therefore, you draw this arrow going this way. For nonmetals, you say increasing melting and boiling point. Increasing melting and boiling point for nonmetals. Yes. So we have discussed these 4 things: melting and boiling points, electrical conductivity. In this video we have talked about these 2. In another video there was a discussion of these 2. And in yet the very first video we discussed the periodic table to understand how it is written, the various elements and the atomic size and atomic radius. So if you have any question on the periodic table, please comment below, or you follow up on my WhatsApp in the details in this channel, or you can ask for a one-on-one online tuition, and we'll be sure to explain to you in detail, and especially if you have personal questions or yes. So again, as I always reiterate, the best thing you can ever do to this teacher, creator, is to subscribe to my channel. Please, take a moment, just subscribe. Just hit that subscribe button, and I really appreciate, and to give me consistency to continue uploading more helpful videos on this channel. See you in the next video. Thank you, and all the best in your exams and your careers.